Notes will be over page 38 through 40. Okay, so we're going to start with comparing graphs. So sketch the shape of each type of graph, then draw a diagram to represent the type of motion. Okay, I'm going to start out with a key. So this is going to be our negative direction. This will be our positive direction. Okay, and then a flag will be our reference point. Okay, so the first is stopped. And so for the stopped motion, for a position versus time graph, so we have our position and time, position and time. Okay, so remember, if it is stopped, it's going to have a horizontal line or a zero sloped line. So if it's in the positive position, it would be above time t, the line time t, or we could have it in the negative position. My lines aren't very straight, but hopefully you can make yours a bit more straight. Okay, for a velocity versus time graph, so vt, vt, okay. If it's stopped, it's going to have a velocity of 0, so it will be on the y-axis located at 0. Okay, so for the diagram of this, we have our reference points. Okay, for the first graph, the person is in the positive direction stopped. Okay, and then for the second, the person is in the negative position stopped. Okay, for constant velocity, we're going to have a straight slope. Okay, so we could have a positive slope like this. Okay, so if we have our reference point, the person's actually starting away from the reference point in the positive direction, and they're going to be moving away from the reference point in the positive direction at a constant velocity. Okay, and so if they're moving at a constant velocity, we will have no slope, because remember, a slope on a velocity versus time graph would be acceleration, and this person's going at a constant velocity. Okay, and then we could also have the person going in the opposite direction in constant speed. So they would have a negative velocity, meaning that they're going in the opposite direction or the negative direction. So if we have our reference point, the person is actually starting away from the reference point in the negative direction, and they're going to be moving at constant speed away from the reference point. Okay, for speeding up, okay, our velocity is changing over time. Okay, and so we represent this with a curved line or parabola, okay, or we can have going from a stopped position, and then our velocity is increasing. Okay, so if we have our reference point, this person's starting a bit away from the reference point. Okay, and so they are, over time, getting faster in the positive direction. Right, and then for the negative direction, we have this. Okay. This person I had actually start at the reference point, and they are going to be running and the negative direction, getting faster as they go. Okay? For slowing down, okay, our parabola is going to start out steep and then get more shallow. The tangent lines will become more shallow until they reach the horizontal. So for TT, all right. And so for this, we're going from a higher velocity down to 0. So we're stopping. And so if we were to show this, they're in the positive direction. And so they were going fast, and then they're slowing down as they go on. Okay? And then for the negative direction, start at a higher velocity and go to 0 or stop. Okay, so their position is to the negative side. And they were going fast, and they are slowing down over time. Okay, so we're just going to do a few practice questions together. So a car waits at a red light for 12 seconds, then accelerates north at a constant rate up to a 16 meters per second over 4 seconds. The car maintains that constant velocity for 15 seconds. Okay, so we're going to draw a position versus time graph. All right, so we have 0.00. And so our first time in seconds, and then this will be in meters north. Okay, our first time stamp that they gave us is that the car waits at a red light for 12 seconds. Okay, it then says it accelerates north at a constant rate up to 16 meters per second over 4 seconds. So 12 plus 4 seconds would give us 16 seconds. And then it says the car maintains that constant velocity for another 15 seconds. So 15 seconds more would give us 31 seconds. All right, so drawing in the graph, their position, since they're stopped at the red light, that's going to be our reference point. We're going to stay here for 12 seconds. Then they're going to accelerate for 4 seconds up to 16 meters per second. So it's going to be a parabola. Okay, and then they're going to maintain that for another 31. Okay, so it's going to be straight. All right, so then for a velocity versus time graph, then it's going to be in meters per second north. Okay, we're going to have the same timestamps, so 12 seconds, 16 seconds, and then 31. Okay, but they did give us a constant rate of 16 meters per second in 4 seconds. Okay, so when they're stopped, the velocity would have been at 0. Okay, then they're going to accelerate north at a constant rate up to 16. So we're going to have slope. Okay, and then they're going to maintain constant velocity. So there's no acceleration. So it's going to be a zero sloped line. For number 2, an ambulance is traveling at a constant velocity of 14 meters per second east. After a short time, the ambulance driver receives a message to attend to an emergency. The ambulance quickly decelerates to a stop, turns around, and accelerates to 22 meters per second. Okay, so they don't actually give us timestamps on this, but we'll go ahead and just kind of draw some in. Okay, so this is in time, and they didn't give us, I guess it would be in seconds. And then our position in meters, we'll say east, because that's the first direction they started in. Okay, so here's 0. Okay, so it says an ambulance is traveling at a constant velocity. After a short time, the ambulance driver receives a message to attend to an emergency. The ambulance quickly decelerates, stops, and then turns around and accelerates to 22 meters per second west. Okay, so here would be whenever they get the message, they start to slow down. They actually quickly stops and turns around and then accelerates until they get to 22 meters per second west. Okay, so drawing in the line from our starting position. Okay, they're moving in the east direction at a constant rate. Okay, this is when he gets the message, so he's going to slow down until he stops. So that'll be the top of our parabola. And then he's going to speed up until he gets to the 22 meters per second west, and then continue on at that constant speed. Okay, for the velocity versus time graph, and then our velocity is in meters per second east. Okay, once again, we're going to have the same timestamps, even though they're made up. Okay, so they started out at 14 meters per second and then eventually got to 22 in the opposite direction. Okay, so they were going at a constant speed until he got the message, and then he slowed down till he came to a stop, crossing that 0 mark, and then accelerated until he got to 22 meters per second in the opposite direction, and then had a constant velocity from there. For question number 3, a dog plays fetch. The dog accelerates towards a ball, decelerates to a stop to receive the ball, then accelerates back towards its owner, and decelerates to a stop as it reaches the owner. Okay, so we have quite a few things that are happening here. So time, we'll just say seconds. They don't really give us any units here. And we could say this is meters north. Okay, so they're going to accelerate towards the ball. So this is their acceleration mark. And then they're going to begin to decelerate to stop to get the ball. And then they're going to accelerate back towards the owner, and then they're going to decelerate once they reach the owner. Okay, so those are all the marks that we're going to have to go. Okay, so we have acceleration, then we have deceleration until we come to a stop, and then we have acceleration but in the negative direction, and then we're going to have deceleration where they're slowing down again. Okay, for the velocity versus time graph, we've got time and velocity. Okay, same marks. So 1, 2, 3, 4. So they're going to accelerate towards the ball, and then they're going to have to slow down until they reach the ball and stop. Okay, and then they're going to start going back, accelerating towards the owner, and then slowing back down until they stop at the owner. Okay, for this next part, deriving the 5 equations of kinematics, we're actually not going to go through all of the deriving parts of it just because it is a bit tedious and it's not as important as actually being able to apply the actual equations. So we're going to go through this page, page 40, and it'll just be an introduction into the notes that we'll be taking here shortly. Okay, so there are 5 main equations of kinematics that involve 5 different variables. So we're going to identify the different variables. So the first one, the change of position, is going to be displacement. D1 is going to be the initial velocity. Okay, that should be familiar from our previous notes. V2 is going to be our final velocity. A is going to be acceleration. And then delta T is going to be elapsed time or change in time. Okay, so the following 5 equations are useful for situations involving constant acceleration. If a problem involves constant velocity, these equations should not be used, and you would use this instead. Okay, so that's if our velocity is constant. Okay, so for each of these problems, we're going to look at what is given to us. Okay, so for this first one, we have V2, we have V1, we have A, and delta T. Okay, for the next one, we have displacement, we have final velocity, initial velocity, and time t, or delta t. For the next, we have displacement, we have v1, acceleration, and time. For this one, we have displacement, final velocity, time, and acceleration. And then for the last one, we have final velocity, initial velocity, acceleration, and displacement. Okay, so what you should notice is that each equation involves 4 of the 5 possible variables. So one is going to be excluded from each equation. So it uses 4 of the 5 variables. 1 excluded. Okay, and so we're going to get more into actually using these equations, but it's important to note that you only need 4 pieces of the equation to find out one of the missing variables.